Cat, your friendly chemistry tutor.
The Lewis theory on acids and bases. In the last video, we talked about the Bronsted-Lowry theory, where acids and bases throw protons around like a ball of yarn. That was all fun and games, until this dude called Gilbert Lewis walked in the room and said, "Forget protons, we're talking electrons now." The Lewis theory of acids and bases is all about electrons being donated or accepted. A Lewis base is electron-rich, which makes it an electron donor. It gives away an electron and becomes less negative. A Lewis acid is electron-poor, which makes it an electron acceptor. It takes an electron and becomes more negative. This exchange results in a new molecule or complex being formed. You want to start with identifying who is electron-poor versus who is electron-rich. Some atoms are electron-poor because they are bonded to very electronegative atoms that pull all the electron density towards them. Also, the electron-poor atoms must be willing to accept electrons. On the left here, not only are the fluorine pulling electron density away from boron, but boron also does not have a full octet, so it is very willing to accept electrons. Some atoms are electron-rich because they have lone pairs or negative charges, indicating a surplus of electrons. On the right here, phosphorus has a lone pair of electrons sitting on its head, so it definitely has electrons to donate. Imagine this. It's a late afternoon at the Cozy Cat Cafe. Two cats are chilling and scrolling on their phones while sipping on some milk. One cat's phone is fully charged. This cat is the Lewis base, and it's electron-rich. The other cat's phone just fully died. This cat is the Lewis acid, and it's electron-poor. As you guessed, the phone battery represents electrons. Panic sets in. The cat with the dead phone wants to continue doom scrolling. So, he lovingly asks the other cat in the cafe with a charged phone to share some battery with him. The cat with the charged phone is kind, so she says yes. She connects both of their phones with a charging cable so that some of her battery can start transferring over to this other cat's dead phone. Soon after, the dead phone turns on. Now, both of them are back to doom scrolling and watching silly cat videos on their phones. Let's look at this example over here. H+, or the hydrogen ion, with Cl- or the chlorine ion. H+ with a positive charge indicates a lack of electrons, so it's electron-poor and probably the Lewis acid. Whereas Cl- with its negative charge indicates a surplus of electrons, so it's electron-rich and the Lewis base. Here, chlorine can donate some of its extra electrons to hydrogen, and together they form HCl as the product. Here is a second example involving carbon dioxide or CO2 and water or H2O. The carbon in CO2 is electron-poor because the two oxygens are pulling electron density away from it. So CO2 is the Lewis acid. In H2O, the oxygens have lone pairs on them that are electron-rich and can be used to form bonds, so H2O is the Lewis base. The product of this exchange is H2CO3. You may be wondering why H2O is not the Lewis acid here, because the hydrogens must be feeling electron-poor too, being bonded to the big electronegative oxygen itself. Good thinking. But remember that hydrogens do not have any room to accept more electrons because they prefer being in a duet. Let's see what you've learned so far. Identify the Lewis acid and base below, then draw the product of their exchange. Please pause the video and return when you are ready. Welcome back! It always helps to draw out the Lewis structures of all molecules to see the electron distribution properly. Remember that the Lewis acid is electron-poor, and the sulfur in SO3 has 3 electronegative oxygens pulling electron density away from it. So, SO3 is the Lewis acid. Looking at C5H5N, there is a lone pair of electrons on nitrogen, meaning it's electron-rich, So, this molecule is definitely the Lewis base. For the product, the electron-rich nitrogen will form a bond with the electron-poor sulfur, right here. Now, the formal charge on nitrogen will be positive, and the formal charge on sulfur will be negative. You did it! Here is an updated and fixed chart that highlights the differences between the Bronsted-Lowry theory and Lewis theory on acids and bases. Feel free to take a screenshot. Thanks for watching. You can find a free full-size worksheet about the Bronsted-Lowry theory versus the Lewis theory on acids and bases on ChemCat's Payhip page linked in the description below. If you have any questions, feel free to email me at chemcat786@gmail.com. And as always, please like and subscribe to support this channel.